Hello students, today we are going to see what are the symmetry operations in the particle physics. So see here, basically symmetry operations are relative to the conservation laws. There is a strong correlation between the symmetry operations and the conservation laws. Okay, for example, if you consider any system and if that system is invariant under the time, then you can say that that system follows the law of conservation of the energy. I'll write it here. So what I'm trying to tell you that if there is an invariance under time, then this corresponds to the conservation of the energy. Similarly, if any system is invariant under the translation in space, then that system is said to have, or it is said to possess, the law of conservation of linear momentum. See here, if there is invariance in a translation in space, so the system is supposed to follow the law of conservation of linear momentum. Now if there is any system which is invariant under the rotational motion, then it is supposed to follow the law of conservation of the angular momentum. Now see here, if there is an invariance under the rotational motion, then the system is supposed to follow the law of conservation of the angular momentum. Conservation of, like this, we can say that these symmetry operations are very much similar to the law of conservation of the energy, linear momentum and angular momentum, or the symmetry operations corresponds to the conservation laws. If you suppose, if you consider any system, and if that system is invariant means if it remains unchanged under the time, then that will follow the law of conservation of energy. If that system remains unchanged under the translation motion in a space, then that will definitely follow the law of conservation of the linear momentum. And if the system remains unchanged in a rotational motion, if it remains invariant under the rotational motion, then it is supposed to follow the law of conservation of the angular momentum. Okay, now see here, today we are going to deal with the symmetry operations in a particle physics. Now in a particle physics, we mainly deal with the strong nuclear force and a weak nuclear force. I'll write it here. Actually I have already written here. So before coming to the particle physics, we were just knowing that the protons has a positivity charge and neutron is a neutral. But now when we know the constitution of the proton, we know that it is made up of 2 up quarks and 1 down quark, whereas this neutron is made up of 2 down quarks and 1 up quark. Now according to the electrodynamic theory, quantum electrodynamic theory or quantum chromodynamic theory, I have written these two theories over here. So what these theories says that whenever there is interaction between any two bodies, there must be exchange of some particle. For example, there is a force of attraction between the sun and the earth. Okay. Now according to the quantum electrodynamic theory, it says that if there is a force of attraction between any two bodies, there must be some exchange of that particle. So that particle is called as a gauge boson. Okay, so that exchange particle must be there. Then and then only then these two particles can have attraction or interaction. Okay, whether these two particles will have interaction, whether it is attractive force or the repulsive force. So this is what the quantum electrodynamic theory says, or the quantum chromodynamic theory says that when two quarks are there, these two quarks are interacting via the colors. Okay, so colors are, they have nothing to deal with our day-to-day colors, even if they are named as red, blue and green. Okay, so let me first tell you that this proton is made up of up and down quark, and this neutron is made up of down and up quark. So whenever there is an interaction between a proton and neutron, now we know that in a nucleus, so large, now this is a image of the nucleus, and it will consist of large number of protons and neutrons. See here, this is a classical picture of the nucleus. Actually, nucleus is a quantum mechanical entity. It doesn't look like this exactly, okay, but for our understanding, sake of understanding, we are taking it like this. Okay, so we know that the neutron, if the nucleus is there, and if the heavy nucleus is there, it will consist of large number of protons and neutrons, okay, and there must be some interaction between these protons and neutrons, okay. So according to the quantum electrodynamic theory, whenever there is interaction between any two particles, that interaction must be due to some exchange of that particle, okay. Now this exchange particle in a proton and a neutron, it is called as a pion. Let me write it here. So this is a pion. Now we know that this proton is again made up of quarks. Okay, so inside the proton, 2 up quarks and 1 down quark is present. Okay, and quarks are also particles, and whenever there is interaction between any two particles, means the quarks are again bound with each other inside the proton. So there must be some interaction particle, there must be some gauge boson must be present, and the gauge boson, which is responsible for the strong nuclear interaction between these two quarks, it is called as a gluon. So let me write it here. So this is the gluon. Okay. Now see here, if we have already seen what is a weak nuclear interaction. So whenever there is a beta decay, plus beta decay and minus beta decay, these are the examples of the weak nuclear interaction which we have already dealt with in my previous videos, okay. So suppose if there is a particle which is having excess amount of energy, it will try to attain the stability by this beta decay process, okay. And what happens in this beta decay process? So this proton can be converted into the neutron, or the neutron can be converted into the proton. So we have taken one example of proton converted itself to the neutron. Now see here, so this is a proton, up and down quark, and it has converted to the neutron, which is a down and up quark. So actually when we see that only one up quark has changed to the one down quark, and this up quark, they have remained same, this down quark has remained the same, okay. So only there is a conversion of one up quark to the one down quark, and there is an emission of this positron and this positron neutrino, okay. Now see here, so this is a Feynman diagram explaining the weak nuclear interaction. So which says that from a up quark, it converts itself to the down quark along with this up and anti-down quark, it is present over. So this particle, this is nothing but the pion. So we can say that when this proton is converted to the neutron, so this interaction is mediated by the pion particle. So the gauge boson for this weak nuclear interaction is a pion, okay. So we have already seen the constitution of the pi minus. So this is a pi minus, okay. So up quark, this is 2 by 3, and down quark, this is a plus 1 by 3, minus of minus 1 by 3. I'll write it here like this. Down quark has a charge of minus 1 by 3. So it will be 1 plus 1. So this is pi plus, sorry. So we have taken the beta plus decay. So this is a pi plus, okay. Now see here, what I am trying to say is that, so whenever there is a conversion of proton into the neutron to attain the stability, so it gives us the so that interaction is mediated by this pion, and this pion is nothing but the one up quark and anti-down quark. We know that the pion is a type of a meson, and mesons are made up of one quark and one anti-quark, okay. Now basically when we deal with the weak nuclear interactions, so they are generally mediated by the combination of this up quark and the down quark only. Similarly, if we deal with a strong nuclear interaction, as I already said that whenever there is a strong interaction between the two down quarks or two up quarks, so that is mediated by a gluon. Okay, now this is the Feynman diagram for that strong nuclear interaction, and here you can see that. So this red color, now let me tell you that the colors are nothing but they are also particles like up quark and down quark. Okay, the particles with the different properties like different spin and angular momentum, linear momentum, etc, etc. Okay, they have nothing to do with the regular colors like red, blue and green. Okay, so there are three types of particles which are exchange bosons for the interaction between the quarks. Okay, now see here, so there are three types of particles or the three types of the colors, and they will also have the anti-particles like anti-red, anti-blue and anti-green. Okay, now we can see here whenever there is a strong nuclear interaction in which this red color is converted into the blue color by giving out this R and B. Now this particle is called as a gluon. Okay, so a large number of possible combinations are there for gluons. So this will have antiparticles also, but basically three colors are there. So charm cork, strange cork, top cork and bottom cork are just the heavier versions of the up cork and down cork. Okay, as we can see that only two particles are involved for the weak nuclear interaction, whereas the three particles are involved for the strong nuclear interactions. Therefore, we are using the SU2 symmetry for the representation or the mathematical representation of the weak nuclear interaction, whereas we are using the SU3 symmetry for the strong nuclear interaction. Okay, for the representation of the strong nuclear interaction. So here I have written so SU2 and SU3. So this is nothing but the special unitary matrix of 2 by 2, and this is the special unitary matrix of 3 by 3. Okay, so special unitary matrix means the matrix which is having the determinant is equal to 1 and trace is equal to 0. Trace is nothing but the addition of the elements in the diagonal, that must be equal to 0. Let me write the condition over here. So determinant M is equal to 1 and trace is equal to 0. So such a type of matrices are called as a special unitary matrix. And as we have seen that the weak nuclear interaction can be represented by two basic particles, therefore we are using this 2 by 2 special unitary matrix for the mathematical representation of the weak nuclear interaction. And similarly, three basic particles are involved in a strong nuclear interaction. Therefore, we are using the SU3 symmetry operations for the mathematical representation of the strong nuclear interaction. Okay, now the Pauli's matrices are good examples of the SU2 symmetries which are generally used to calculate the electron spin in x, y and z directions. Okay, they are represented by sigma x, sigma y and sigma z like that. Okay, now if suppose if the alpha is a probability amplitude of a up quark, we have assigned some name alpha, which is a probability amplitude of the up quark, and the probability amplitude of the down quark is, let's say, beta. Okay, now if we are considering some state and if we are operating it with some Pauli's matrix, it will give us a new state of alpha dash and beta dash. Okay, so this is nothing but the mathematical representation of the symmetry operations in a particle physics. Okay, so this is the representation of the symmetry operations for the weak nuclear interaction. Similarly, as we have seen that the three basic particles are involved in a strong nuclear interaction. So SU3 special unitary matrix of 3 by 3, and I have given an example. So the trace is 0 and the magnitude will be 1. So different 8 to 9 types of the matrices can be formed to give out the conditions or to satisfy this condition. So determinant is equal to 1 and trace is equal to 0. Okay, so if I say that as a lambda, and now suppose now this is a probability amplitude for the, we have taken the wave functions, yes, quantum mechanics. Okay, now if psi r is a probability amplitude for the red color, psi b is a probability amplitude for the blue color, and psi g is a probability amplitude for the green color, and if we are operating it by the SU3 symmetry matrix, okay, then we are going to get a new state for the gluon. In these symmetry operations, which corresponds to the law of conservations of the energy, momentum, linear momentum and angular momentum, we can say that there are 4 basic forces in the universe, like starting from a weak force, the gravitational force, then electromagnetic force, weak nuclear force and strong nuclear force. So the strong nuclear force is represented by SU3, this can be represented by SU2, this can be represented by the unitary matrix 1 by 1. So moral of the story is that SU3 and SU2 operations can represent the conservation laws in a particle physics. Thank you for watching.